Oh yes. So yeah. Some of you have asked me, what are we doing this week's seminar? I want to prepare, etc., etc. And I never answered because the truth is I don't know. I usually I found out yesterday at 6 that for sure I'm holding this seminar, and I wasn't assigned something to go over. That being said, I finished the grading in the meantime, and I think the results should be posted today. I have no idea. I've been done for a good couple of days, but I guess somebody had extension or something. I don't know. Anyway, yeah, and unfortunately, I think a lot of people had some problems with the Kant-Tucker method, which I think is the quintessential thing that you learned in Math 2 since you started this semester, like Lagrangian and Kant-Tucker. That's basically what you learned. And then critical points. Those are the two big things. Now, I could technically cover seminar 4 from the regular group, which just showcases the envelope theorem in some weird way. So let's just do a raise of hands. How many of you would like me to go over, let's just say, I don't know, seminar 4? And how many of you would like to, I was thinking maybe just do some exam problems for the past years that had Kant-Tucker in it. So let's do, how many of you want me to do seminar 4? Okay, so unfortunately, it's not really democracy, and technically I am scheduled to do that. So I'm just gonna go through it, I guess in a faster way, and then for the second half, we're gonna do 1, maybe 2 problems on from the past exams that actually use Lagrangian and Kant-Tucker. I think the past exams this year are not as relevant, I guess, as they were last year. For example, last year I could have told you more or less what's gonna be on the exam, just because all the exams are so exactly the same. You had a problem from derivatives, a problem from Lagrangian, a problem from that, and they were all kind of the same. But the professor changed from last year in the last couple of years. So I don't really know what to expect this year. As a result, let's just start with seminar 4, I guess. And then we'll do some past exams. But I really want to do some Kant-Tucker and Lagrangian, I guess, somewhat more complicated with more constraints, because I think a problem that I've seen a lot is that when you had the budget constraint, which was equal, and you had another constraint, which was the Kant-Tucker constraint, in the assignment, for example, some people, when they were writing in the Kant-Tucker, they conditioned both lambdas, which is a big mistake. So we'll go over that in an example. But let's start with seminar 4. So give me 1 second to actually remember how this looks. Oh yeah, okay. So I'm just going to copy it and I'm going to show you what I wrote. There's a weird phrasing on problem number 1. So you are given this E of P1, P2 equal to minimizing P1 x1 plus P2 x2, subject to U of x1, x2, whatever. Okay, and now they're basically saying for some utility function, the expenditure function is defined as whatever. What he means is that once you find optimal P from up top, P1 star, P2 star, if you plug it in. Sorry. Yeah. Right a little bit there. If you plug it in the expenditure function, you get the relationship they're giving it, but it's not really clear from the phrasing. But ideally is that, you know, the expenditure function that I'm going to write now, which is this thing, is like the solution expenditure function. Okay. So it would be E of P1, P2, and the U bar is equal to this. U bar. Okay, and now they're asking us to show using derivative from, you know, find expression for derivative using star to the first one, derivative using the second, and then combine to get a solution, blah, blah, blah. Okay. So this problem is specifically made to show the envelope here. Okay, it's like, it's just constructed for this. Now, you might find this is, oh my God, this is so powerful, and I'm gonna use it from now. I never need to compute anything. I'm just gonna use the envelope theorem. That is wrong. In my, I don't know, a lot of math, I have not seen a problem when you're given this thing. Okay, and when you're not given the solution, but you're given the solution expenditure function, that is something so specific that I've not seen in a lot of problems. Now, could envelope theorem pop up on the exam? Yes, but I don't know, from the last 10 years and judging from what I think, it would just be like a point F or a point E or something. It wouldn't be like a problem constructed to be solved only by the envelope theorem. The reason being is that you have a lot of other stuff like linear algebra, limits, integrals, and whatever. So you have a lot of other way more important material. But let's just do this problem. So I am asked on point A from this equation, from the first one, or, you know, the first problem, I'm asked to compute, you know, I like writing it like this, derivative of E with respect to derivative of P1. And now it might be tempting to take a derivative of just this thing, of just the equation, and say this is it, which is absolutely wrong. The reason being is that this is a problem, okay? This is not an equation. This E of P1 is a problem. You're asked to minimize over this. So when you replace X1 and whatever, it's gonna look totally different. Now, the envelope theorem just says in like a constrained optimization, the easiest way to remember it is that this is just equal to the derivative of the associated Lagrangian with respect to P1. All right? This is the envelope theorem in its simplest way. It's just, if you have a constraint, taking the derivative of this is just the same as taking the derivative of the associated Lagrangian. So the associated Lagrangian is L is just equal to, you know, P1 x1 plus P2 x2 minus lambda U x1 x2 minus U bar. Now, you are not asked to solve it because you can't solve it. You're just going to take derivative. Okay, you're just going to say, okay, they asked me to compute derivative of E with respect to P1, which again, really careful. And it's I've asked for it, but this is minimizing over x1, x2. These are the values that you need to find out. P1 and P2 are given as constants, okay? But now we're just asking you to take a derivative of this. So, you know, this is just equal to the derivative of the Lagrangian. And this is pretty important. This is evaluated at like x1 star, x2 star, okay? So I'll show you what I mean by this. I'm just going to write the derivative of the Lagrangian with respect to P1, and that is just x1. Yeah, x1, this is 0, you know, 0, 0. The nice thing about this is that this U of x1, x2, which is so enigmatic and you have no idea what it is, does not depend on P1, okay? So when you take a derivative, it just disappears. That's the whole idea of this problem. And basically, you just get an x1, and I said you need to evaluate this at x1 star, so this is just x1 star. Okay? Again, the envelope theorem in its simplest version is this one. Okay? That is what you need to use. Now, for point number 2, they're telling us, okay, compute the derivative of this equation with respect to P1. So, I mean, there's not much I can do other than just compute it. So what do I get? I get derivative of E with respect to P1. I'm going to copy it here so it looks nicer. U bar, derivative of P1. And this is just, this is P1, everything else is constant. So this is just alpha, P1, alpha minus 1, K, P2, 1 minus alpha, U bar. Okay. And now, the whole idea of the problem, showing you the envelope theorem, is that you have computed. So first of all, in point 2, I'm just moving fast because I didn't do much. I just took the derivative of the given function. Okay, there's not much I did there. So now the whole idea is that I have computed the same exact derivative in 2 different ways. Okay, so as you would write for the lambda, I guess, or I've seen it, derivative of E with respect to P1 is equal to derivative of E with respect to P1. So this is just the same as saying X1 star is equal to this thing. And you have solved the system in this amazing, glorious way in two lines. Okay. Now, I remember, take this with a grain of salt. I said it from the start. This problem was constructed to be solved like this. It is not, I mean, at this point, I think you guys have done a decent amount on the Lagrangian problems. You've never been given this. You've never been given like the solution expenditure function and then asked to solve it. So it's a little bit backwards, but still, there are problems where you might be asked something like, compute this derivative, and you can keep in mind that you can just use the Lagrangian, or you can just use the Lagrangian for it. So that's the only thing I would keep from here. If there are no questions, I'm just going to move to problem number 10, which was a computational pain for a lot of people. So I'm just going to move on if there are no questions. Again, envelope theorem, keep it in the back of your head. This is it in the simplest forms. In that simplest form. One thing that some people overlook, but I think it's pretty important, is that this, this derivative is evaluated at the solution. Okay, so as you see, you compute the derivative, and then you just put it the solution, which is just putting it a star there, kind of thing. Okay, that's pretty important. In some cases, might matter. In this case, it didn't matter. That's why I think that we could have showcased a little bit the strength of the envelope theorem a little bit better. Because if you just didn't really understand what the problem was telling you, and you would just randomly take a derivative of this thing over here, which I said is wrong, just taking the derivative of this, you would still get the same result, which is just not okay. I would have given something that makes it more complicated, just to show you that it's not okay to do that. Anyway, let's do problem number 10, because there's a lot of computation in it, which I would say that if I were to sum up this, the main problem I've seen through the papers is actually computation issues. That's why I think on the current assignments on seminars, on the workshops, the professor has actually given like a little bit easier problems, because I think he realized that the computation is actually part of what's killing some people. Some people write the equations perfectly, and then they just get lost in the computation. And it's just sad, it's just sad to know the theory and then just get stuck in like 3 lines of work, basically. So yeah, that is like, I guess, another big problem. Problem number 10. Let me bring it up 1 second. I should have memorized it by now, I know. Oh yeah, it's big, yeah, I can't memorize it. Okay, so I'm gonna copy everything and then I'll show you A plus B, B. Okay. B. Okay. Okay, and the solutions, we're not going to cheat from now on. We're not going to, we're pretending we don't know the solutions. Okay, so this is the problem. First question is, where is U defined? This is more or less asking for the domain, which is just a fancy term for asking, can I just put any whatever numbers I want here instead of X and Y? That is just what it's asking. And you just look at it, you have a log, which whenever you see a log, you should think that this is, a log of, X does not exist if X is smaller or equal to 0. It just, you can't define it. So the only constraint you can see here is that X minus A, what's inside the log here has to be greater than 0, and Y minus B has to be greater than 0. So these are all the restrictions. Yeah, there's nothing else. You should, for example, it's not that hard. Obviously, if you had 1 over X or something, you could add the condition that X can't be 0 or those type of conditions. Just when they're asking you where is U defined, just think it simple. Where does this function make sense? Okay, just pick the simplest thing out. Okay, now in point B, they're asking us to maximize over X, Y of this thing. It's not there. Be subject to P again. Okay. All right, let's go out so we don't die. Okay, so now that we saved ourselves from the fire, we can keep going. It's so great, everyone wants to come at 8 a.m. to do math, and they decide to put a fire alarm to make it even better. I'll never understand. Anyway, so we have to maximize this problem subject to Px plus Qy is equal to R. And I know it has to be equal to some sort of formula that the problem gives you, but we'll deal with that afterwards, okay? For now, I'm just interested in setting up my Lagrangian. And then basically, I'm just saying I'll see what happens when I get there. Okay. I have one comment though. My only comment is that whenever you see a problem that says, solve this problem and then show that the solution is of this form, when you're solving it by hand, you're never going to get this form straight out of, just I computed it and I automatically got this. No, this is just some idea that I guess the authors had in mind when they wrote it like this, okay? But this is not how your solution is going to look. This is not how my solution is going to look after I compute it. So it's just a matter of changing it afterwards. But priority is to compute the solution for myself. So you know the drill by now. I just compute the derivative, and I get A times 1 over X minus A minus lambda plus lambda P, I guess, equals to 0. Derivative of Y, A of B, 1, Y minus B, plus lambda Q is equal to 0. And you have the last one, derivative of lambda of L with respect to lambda, which is just your constraint. Now, I've said it before, and I think for those of you that actually listen, I'm sorry if I'm repeating myself, but you'd write this derivative, the derivative with respect to lambda, if you have an equal sign, okay? If there's an equal sign here, you can write the derivative with respect to lambda. If you had this sign, do not write the derivative with respect to lambda, because if you had that sign and you write the derivative to lambda, you're just going to get from the first derivative that it has to be equal to 0, which is not true. So what I'm saying, again, is you can write this derivative with respect to lambda, which is part of the Lagrangian, if it is equal. If it's not, if it's equal right now, right here, this would be equal here. If it's equal, you can write this derivative. If it's not equal, then do not write this derivative, okay? Because obviously, it's gonna just give you equality here. So that is one thing that I wanted to address. Now, how to solve this thing? Yeah, I don't know. I'm thinking maybe I can find something an easier way to do, but I just can't find it. So what I'm going to do is just express, I will have that, minus lambda is equal to a times 1 px minus a, minus lambda here is equal to b times 1 q y minus b. In case it's confusing what I did, I just moved this to the other side and I divided by p and q respectively. Okay, so I'm gonna do much. And now, as somebody would say, minus lambda is equal to minus lambda. I kind of like that writing. I don't know why. Minus lambda is equal to minus lambda. So I have a times 1 px minus a is equal to b times 1 q y minus b. Okay, now I'm just gonna express x in terms of y. It doesn't really matter. So what do I get? I just get b times p times x minus a is equal to a times q times y minus b. In case it wasn't clear, I'm just doing products like this. And now I said I'm just going to express my x minus my x in terms of y. So I get x minus a is equal to a q y minus b over b p. Okay. And now, x is just equal to this thing. B of p plus a. Again, another comment which I've seen it more and more, is that writing your answers in terms of lambda, like having, I don't know, your solution in terms of lambda is not what the problem is asking you. The problem is asking you to maximize over x and y. So what you need in order to solve this problem is give me x is equal to something, y is equal to something. And then second claim, you can't tell me x is equal to this times y. Okay, it needs to be expressed in something that you could compute. You can't just write x is equal to this and y is equal to whatever in terms of x. Okay, you need to solve it. So this is another claim, because I think somebody actually presented me this result in the last problem, 2f or something like that, and then said it was quite easy. So it was quite, yeah. Moving on. I don't know exactly what comment to write there. So yeah, now let's just replace this x in the budget constraint, and I would have r is equal to p times all this ugly thing. No, sorry. A q y minus b bp plus a plus q times y. Okay, this looks worse than I remember. Okay, so let's see what we get. First of all, I'm just going to multiply everything here, so I get aq y minus b, b plus PA plus QY. Okay? Now, I'm just going to compute it and say R is equal to AQY. So I'm just opening this parenthesis, okay? AQI minus AQB over big B plus P of A plus QY. Okay, it's getting better, kind of. So now I see that I have a QI, so I just factor it out and I get R is equal to QY, and I have an A over B plus 1 from here, right? Minus AQD over B plus PA. Oh. Okay. So I hope my computation wasn't too whatever at this point. Now, this 1 is just B over B. So what I get is what I'm getting is, if the camera would focus, yeah. I'm getting R is equal to QY, A plus B over B, minus AQB over B plus PA. Okay, now let's multiply everything by B. And remember, this is 1. The problem tells you that A plus B is equal to 1. So that is 1. So I just get RB is equal to QY minus AQB plus PA big B. Okay, so now Y is just equal to my formula, which I know we're going to say it doesn't look anything like the one in the book. Minus PAB, everything over Q. Okay? Looks like something. All right. So this is my result. And the reason I can leave it like this is, again, if the problem wanted me to give numbers, if they had to give me R, B, Q, E, basically everything, so I can just compute this. I will get a value for this. Cool. Now, let's see what they wanted me to get. Their answer looks like this. Y is equal to B plus big B, R minus PA plus QB, Q. Okay? This is what they want me to get, their Y star. You know, Y star from the problem, Y star, my Y star. So now some of you asked me, okay, how do I get from here to here, and started doing these fancy tricks. I'm not as fancy. I'm just gonna say, okay, I'm just gonna check if they're equal. Simple. I'm just gonna see if my answer RB plus AQB minus PAB, everything over Q, is equal to B plus BR minus PA plus QB. Okay, if these two are equal, then it means it's just the same thing, just written differently. Okay, so this is what I'm going to check right now. So first step, I just multiply everything by Q. And I'm going to get RB plus AQ small b minus PA big B is equal to QB plus, let's open these parentheses, maybe we get something, I don't know. BR minus B PA minus B QB, small b. Makes sense? I just opened these parentheses on the right hand side. Okay, let's see. Does anything simplify? This goes away, this goes away. I was expecting more, to be honest. Okay, this goes away. And I'm stuck with these terms. What am I stuck with? I'm stuck with A QB is equal to QB minus BQB. Now, I can just divide by Q and B because B can't be 0 and Q can't, I think they tell you they're strict positive, so I can just divide by them. So I divide by QB, and I get A is equal to 1 minus B, which is true because the problem tells me that A plus B is equal to 1. All right. So I just proved that my solution, although uglier, is the same as theirs. All right. I don't need to do anything fancy. I don't need to like show it that for some mathematical stuff I can get to the form they had. I just needed to check if they're equal. Okay. So that's exactly what I did. Now, I could do the exact same for X, but I think you got the idea. If one of them is correct, I'm assuming the other one is going to be correct as well. Now, that if they're equal, they're the same. Okay, so okay, so they're asking me to show that the solution is equal to this thing. So I just show that my solution is just equal to this thing, and it's just written a different way. The way you could think about it is that I just got, you know, I just got zx plus zy, and they just showed it as zx plus y. That's the way, you know, obviously in a more complicated setting, but that's the way I would think about it. It's just a different way of writing. I just checked if they're equal. I made them equal, kind of thing. I mean, if I would have not gotten something true here, if I would have just gotten something that's not correct, that's not clear, then, you know, my result is not equal to theirs, so it means I made a mistake somewhere. But in this case, I just checked if they're equal. I'm not saying they are equal. I'm just checking if they're equal. Okay? That's kind of the idea. The way it is that, you know, I could use this if and only if sign as I solve the problem, which means that if this is true, this is true. If this is true, this is true, and if this is true, this is true. Okay, that's kind of the idea. Makes kind of sense. So yeah, it's basically just the same quantity, just written differently. Any other questions on this? Again, if they're giving you the answer, and you're asked something like show that the answer is equal to this or something, nothing is stopping you from just checking if your result is equal to that. Okay, there's nothing stopping you from doing that, and that is especially important. That is especially a good trick at integrals. I am proud to say that in like 10 years or whatever, the professors didn't change their problems, but once I got to TA, they had to change their problems because everyone was solving them in one line, which is just checking. They were just checking if it works, and that was full score. It worked for like 3 exams in a row until I think he found out. Because he was like, "Oh, everyone is doing the integrals." I'm like, "Yeah." Okay. What conditions must the constant satisfy? Conditions. X star, Y star, etc., really to solve the problem, draw a diagram. Okay, I'm not going to draw a diagram because it's not going to look nice anyway. And I think it's going to be more confusing. But I can give you the conditions, and I can do even more than that. I can give you how you would draw this budget line. Okay, so I don't know if this is how it's taught here or etc., but how I learned it is basically, okay, if you're asked to show U with respect to R, you are kind of asking for you to express you as a function of R. Shows the domain, yeah, okay. So that's basically what I'm saying. They're asking you to kind of show it how it looks, graph it up. And in that case, I would just do the complete dumb method, which is, okay, I have my X stars, my X star and Y star. I know they're equal to dot, dot, dot. And as you can see in the formulas here, I have an R in the formula. So basically, when I plug this in, my function here, I'm gonna have an R here and here as well. So then I can express U in terms of R. So that's why I'm just gonna plug it in. So my U was U of X, Y was equal to A log of X minus A plus B log of Y minus B. And I know X star, this is where their writing comes into play. Now it makes sense why they asked you to write it this way, just because it's way easier to work with. Let me show you X star. I'm just gonna copy right now, and then I'm gonna A plus A R minus PA plus QB over P, and Y star is equal to, we're just gonna finish this problem, then we're gonna have a break. I think it's like 5 lines from here, so it should be fine. Okay, maybe a little bit more. Okay, so these are the values that he gives us, and then I'm just saying, fine, I'll just plug these in. Now, careful, these X star, so R, P, and Q, and A, and whatever are constants, okay? They're not variables. They're given to you. But once I give you these values, your X stars and your R stars are gonna have different values for different of them, okay? So I mean by basically, if I give you R 100, then X star is gonna have a value. But if I give you R1, X star is gonna have a different value, okay? That's all that I'm saying. So if you've seen the notation, we're gonna see it in the last point of this problem, it's basically, X star depends on R, okay? Because you have the R here. For different values of R, you're gonna have different values of X. It's not that rocket science, I guess. It's just something to help you get your head around. It's really nothing smart. It's just observing the fact that, although R is a constant, your X and Y star are gonna have different values for different values, are gonna have different values for whatever R you give me, okay? Okay. So the idea is that once I replace this U star, I just replace with X star of R and Y star of R, that this U is not going to depend on R. Okay, it's not depending on, I'm not going to have X, Y anywhere. It's going to have R, A, P, Q, all these values. So I'm getting R times, we're going to replace here, log of A plus A R minus PA plus QB, P minus A plus B log of B plus B R minus PA plus QB over Q minus B. Okay, first observation, this goes away, this goes away. And now, the reason I decided to actually do this problem is because a lot of people had problems with the log formula. So I'm going to write them right here. The main log formula that I have ever used are log of AB is equal to log of A plus log of B. Log of A over B is equal to log of A minus log of B. A times log of B, ln again, apologize. I'm using log and ln as interchangeable. I'll let you know if something changes along the way. Okay, A times log ln of B is equal to ln of B to the power of A. And these are, I guess, the only formulas, or 99% of the formulas I've ever used in logs, okay? But really, really important. Because I had the unfortunate surprise of in 1 year, one problem being in law and LNs. And although a lot of kids knew the theory, they didn't know how to work with LN. So they got something completely different. Okay, so what do I have left from this U star? I'm not going to copy it. U star, I have A times, and just have this fraction, okay? Let's look at it. I just have this fraction. So I can just use this formula, AB, okay? So I have, and I can use this and this. I'll use these two. What do I mean? I mean that I'm going to get ln of A R minus PI plus QB minus ln of P. Okay? Just use formula number 2. This is formula number 2. Okay, plus B, and again, ln of B R minus PA plus QB minus ln of Q. Okay. Now, for the last step that I need to do here, before it actually gets really, really nice, is I'm going to use formula number 3, formula number 1. Okay. I'm going to use it right here, because I have A times this whole thing here. Yeah. So I can write this as U star is equal to A ln of A plus ln of R minus PA plus QB minus ln of P plus B and B associated plus ln of R minus PA plus Q of B minus ln of Q. Okay, so you got this whole thing right here. And now you probably or hopefully kind of understand why they chose this way of writing, is because you can factor out this ugly term nicely. Okay, it just appears everywhere. That's the whole idea. So U star is just equal to all these constant terms. Bearing is a constant, but okay, plus B ln B minus B ln Q. So completely irrelevant terms. Plus ln R minus PA plus QB, A plus B, which is just 1. So this is your formula. And now, what is the only condition here that you have? You don't even need to graph anything at this point, because you see that the requirement that the only condition you have is, again, the log condition. What do we know about log? Log of x, x has to be greater than 0. So it means that R has R minus PA plus QB has to be greater than 0, because it's underneath the log. And that's the whole problem. Now, I guess if you would graph it and you could graph it nicely, you would get to the same result. I think my graph would just be more confusing, especially with a pen. So I'm gonna skip that, especially because at this point I don't really need to. I just got the result straight from here. Does it make sense? But yeah, when you get something like this, when you get something that seems to work nice, you should tell yourself, okay, I'm on the right way of solving. Okay. When I saw that these things appear in each of them really, really nice, and when I add them, this adds to 1, and I just get this without anything, I knew that, okay, this is the way the problem is meant to be solved. And it doesn't matter if I made a computation mistake along the way, because I am definitely on the right track, kind of thing. All right, this is point C. And now lastly, point D. Point D can be done in two ways. It's just asking you, okay, this U star, basically what I did by now, this U star of PQR is just equal to U star of X star Y star. And when they write stuff like this, okay, let me show you. When they write stuff like this, they're basically just saying, okay, when you replace your X star and Y star, which we did right here, you know, with these values, when I just replace these values, the U function that we get here, this U star, depends on P, Q, and R. Okay, for different values of P and Q and R, I'm going to get different values of this U star. That's all that this is saying. I'm not redefining anything. I'm just saying that, you know, when whatever, all this U star depends on these fixed but constant value, you know, fixed values. So that's the only thing it's saying. And now it's asking me to compute or to show that derivative of U star with respect to R is greater than 0. This is what it's asking me to do. Now, two methods. One is, since I already computed U star up top and I know this is U star, I can just take the derivative of it. So I just write it out. Derivative of U star with respect to R is going to be equal to, and you see there's no R here. So this is 0. You know, this is 0. This is everything is 0. And I only have to take a derivative of this, which is just going to be 1 over R minus PA plus QB. All right, it's just derivative of log. It's just that, which I know is greater than 0 from here. Okay, problem done. Now, there's another way of solving it using the envelope theorem. So first of all, was this clear? I just took the derivative of the function I got from the previous point. And I know it's greater than 0 because this thing has to be greater than 0 for the log to exist. This is my condition from previously. Okay, and now the second condition is, okay, taking the derivative of this U star with respect to R is the same as taking the derivative of the associated Lagrangian with respect to R. Okay, obviously evaluated X star, Y star. Now, how do we do this? Well, we go back here and I don't know how to show you guys. Anyway, you go back to your Lagrangian right here and you take the derivative of this with respect to R. And you just get, in my case, minus lambda. Now, you can compute minus lambda from here because you know X and everything, and you can just replace X star there and compute lambda and then show that it's greater than 0. I'm not going to do that because I already solved it in my way, which is this. But if you wanted to use the envelope theorem here, you could have used it. Okay. So just lambda evaluated at X star, Y star, which you can easily compute from here. But that is, yeah, that's not how I would have done it. Given how I did the point C, and I already had the formula here for U star, there's no point in complicating myself to get it back to lambda. But again, it's personal taste and do whatever you're comfortable with. Now let's have like a 10-minute break. And after this, we can do like the next problem, like 5 minutes or something, and then one exam problem. I think we should be fine. Okay, so I have one small observation about that envelope theorem. In this case, somebody put my envelope theorem page. Okay, yeah, so I have one comment here with the lambda, with the envelope theorem. In this case, it's quite, it works out pretty easy. But in some cases it might not be this easy. So I said it's equal to minus lambda is equal to this thing. So it would just be equal to A times 1 P X star minus A. Okay, and you know that X has to be greater than A. So this would be positive. Now, in this case, it's pretty simple. So it goes out, it gets pretty simple this way as well. But you got to remember that in general cases, or in some cases, you might need to actually replace X star here to show me that it's greater than 0. In this case, it's enough, okay? In this case, again, how I would have wrote it, like X star greater than A greater than 0, P greater than 0. So this is greater than 0, okay? But again, in some cases, you might need to actually replace this X star. So the solution might not be this obvious. That was just, that is just one small addition that I had to. I didn't want to do it because I thought I had to replace X star. Apparently I didn't. Yeah, that's just one small fill up if you want. Great. Now the last problem, I actually didn't really know if I should do it or not, but I've seen some problems like this before, so I was like, why not? It's a 2-minute problem anyway. So I'm asked to find, so this is problem number 23, and I'm asked elasticity of y with respect to x, given that another function, log of y minus a l n x minus b. I'll show you guys in a second. So let me try to understand what I'm doing here myself. Okay. Okay, so you have this. For what values of x is this function defined? Again, this is so first of all, let's answer this question. For what values is this function defined? Where is this function defined? Okay, so let's just start. X here, log of, x has to be greater than 0. So x has to be greater than 0. That's good. Now, this is fine. It's okay if x has to be greater than 0. Now I need to have an even stronger condition for this part. Okay, because I have log of x. So I need x to be greater than 0. And then I need log of x to be greater than 0. So I need, what is this? I need log of x to be greater than log of 1. So x has to be greater than 1. Okay? Cool. Now, they're asking us elasticity of y with respect to x. And this is just something for you to practice derivatives. This is all this problem is basically asking you to do. So instead of y, I'm just going to write y of x. And what is the elasticity? Elasticity with respect to x of y of x is just equal to x over y of x, derivative of y of x over derivative of yeah, I think that's fine. I thought that's the other way around for a second. Okay, formula for elasticity, which I finally learned by heart with you guys. I've avoided it for a lot of years, but I guess it catches back up. Cool. So now the idea is I have this thing. Let's just take a derivative of log of y. Okay, so I have log of y of x. That's my new thing. And my plan is I'll just take a derivative of this whole thing, like everything. So I have log of y, derivative of log of y of x with respect to x plus, minus derivative of a log of x over derivative of x minus derivative of b log of x squared over derivative of x minus derivative of c log of x dx, and this is still equal to 0. Okay, so now we're just gonna compute this and see how it goes. And surprise, surprise, we're gonna get the correct answer. Okay, so let's just compute this derivative. I'm gonna do it relatively fast because I really want to get to the exam problem. But if you want, you can just do this at home. Okay, and you have my notes, so you're not missing anything. So, what is this derivative? It's just the chain rule, so I get 1 over y of x times the derivative of y of x with respect to x. Okay, chain rule minus derivative of log of x is just a times 1 over x minus this derivative. Okay, so this derivative, you can do it, I guess, in multiple ways. The way I do it is just chain rule again. So this is b times, hopefully I'm not wrong, it will be quite embarrassing, but I think this is it. Okay. It's just the chain rule applied to it. Okay. And then last one, I need to do it, I guess, in 2 steps for this one. So it would be, again, chain rule. So it's c times 1 log of x times 1 over x. Okay, I'm just writing the solutions right now. Feel free to do this at home. They're just derivatives, so if I did something too fast, I apologize. Okay, so now I get that 1 y of x derivative of y of x dx is equal to a times 1x plus 2b log of x times 1 over x plus c 1 like x log of x. Okay, we're looking nice right here. But so this is what I got. This is what I have. And the elasticity was equal to this thing over here. Looks kind of similar. Almost the exact same, right? I'm just missing this x right here. So what do? I just multiply everything by x. And I get the final answer, which is x, y, x, dy, x, dx is equal to a 1 over x, 1 over x times x. I'll just write it up nicely. Plus 2b log of x, 1 over x times x, plus c 1 x log of x times x. This simplifies. Hopefully this is the answer from the book. If not, the book is wrong. I don't know, that's what I tell myself. Okay, cool. Now, if you have any questions on this, otherwise, give me a second to see what problem I like. Let's take this randomly. Ooh. Okay. How about we do this one? Looks nice, right? I don't like that one, to be honest. It's a free constant problem, so that might be really good. Okay. So we're going to do problem 5 from 2019. Shall we look in 220 in the exam last year? I think this is fine. Okay, so I'm asked to maximize y squared plus x minus 1 y subject to x squared plus 18y 45 x greater or equal to 2, y greater or equal to a half. Okay, and now you have state Tucker conditions and show that the sum multiplier must be different than 0 to be satisfied. Okay, now let's solve it. This is our problem. What do we do now? First, I'll reverse these constants. Yeah, let's go right. Now, we write the Lagrangian. I think we use minus in this class, right? I always forget. For the multipliers, you use minus, right? Okay. Again, as you would see in the further classes, you can use whatever. Okay, so we're going to use minus here, and I'm going to try to write it really nicely. I get lambda 1 x squared plus 18y minus 45 minus lambda 2, the second constraint, minus x plus 2 minus lambda 3 minus y plus a half. Okay. Now, what are the Tucker conditions? The Tucker conditions include the derivatives with respect to x and y. So the derivative with respect to L, derivative of L with respect to x is just y minus 2 lambda 1, x from here, plus a lambda 2 from here is equal to 0. Nice. Now, derivative with respect to L with respect to y, and I get 2y plus x minus 1. Okay, this is your first derivative. Then I have minus 18y. That's fine. And then I have plus lambda 3 is equal to 0. Okay, I just took derivatives with respect to each of them. Okay. Now, with x, this is the only term that has x, so I just take a derivative and I get a y. Then from here I have an x squared, so I get 2 lambda 1 x. And from here I get minus lambda 2 times minus 1 plus lambda 2. Okay, for y, same rule applies. I get a 2, y squared is just 2y. X minus 1y is just x minus 1 minus, here's a mistake that nobody actually showed me. I have minus lambda 1 times 18y. I need to take a derivative of y, so I get 18 lambda 1. Okay. And then I only have a y here, and I get minus lambda 3 times minus 1 plus lambda 3. Now, should I take derivative with respect to lambdas? No, because if I take derivative, let's say I take derivative of L with respect to lambda 2, I'm going to get minus x plus 2 is equal to 0, so x is equal to 2. This is false, okay? False. X is greater or equal to 2. It is not equal to 2, okay? So do not take derivatives, do not write this derivatives unless you have equal signs, okay? So this is false, this is wrong. I can't write this. Yes? In the Lagrangian, it's fine. Like,
after each constraint, you have minus, and then you have another.
Oh no, it's just when you're switching the line, it's customary to write the sign every time. Just to be clear, it's not minus minus. It's just it's I'll write it really small here, but I mean, it's this y2 plus x minus 1 y minus lambda 1 dot 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 minus lambda 2 dot 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 minus lambda 3 dot dot dot. Okay, just to be clear, it's just the customary way of writing, putting always the sign. Okay, cool. So am I done? No, I need the actual Kahn-Tucker conditions. And now, gotta be careful here. What is? Okay, so gotta write the Kahn-Tucker conditions. Let's take it step by step for lambda 1. For the first constraint, or whatever you want to call it, but take it easy. So, first of all, I get xy plus 8x squared plus 18y is equal to 45. This implies lambda 1 greater or equal to 0. X squared plus 18y is smaller than 45. Lambda 1 is equal to 0. Now, the reason that I have been writing on several papers, do not write it like write it this way. Do not write it like lambda 1 greater or equal to 0 implies dot dot dot. Lambda 1 is equal to 0 implies dot dot dot. Why? Why am I like spamming you and basically telling you do it, keep doing it this way? It's because if I give you a case, lambda is equal to 0, you don't know in which case to go. You can be here or you can be here because this is greater or equal. If I tell you lambda 1 is equal to 0, you can't tell me anything. Well, if you write it like this, there's absolutely no confusion. Either this sum is smaller or is equal. That is the whole idea. That if you go around writing it like lambda 1 generates this or lambda 1 generates that, it doesn't mean anything. Like it's wrong. Because when you're saying lambda 1 is equal to 0 implies x squared plus 18y smaller than 45, this is wrong. Because lambda can be 0 here as well. Does it make sense? What I'm saying? So this way of writing, I have been really nice and I said write it the other way around in the papers and whatnot, but this is wrong, okay? Because you're basically saying, okay, if lambda 1 is equal to 0, it means the constraint is strict. That is not correct. Lambda 1 can be 0 here in the first case, in which the constraint is just equal. So just don't write it like that. I would prefer writing it, lambda 1 is greater or equal to 0. Lambda 1 is with lambda 1 being 0 if it's strict, but not only if it's strict. Anyway, that it depends. This is how I would advise writing it, especially the way he gives it, just because you can see the two cases really, really clear separately. Okay, this is how I would advise it. Now, however you do it is your choice, but this is how I would advise it. Definitely not like this, because this is wrong. This is bad. Okay, now for lambda 2, and again, the constraints, these things apply to each of their respective conditions. They do not apply to the general. Like for example, if this is equal, it doesn't mean that lambda 1, lambda 2, and lambda 3 have to be greater or equal to 0. They are completely independent. So I'm going to write the case for lambda 2, which is minus x is equal to minus 2. It means lambda 2 is greater or equal to 0. And in these cases, I don't know anything. So I'm actually going to write, I don't know anything. That is a bold statement. About lambda 1, lambda 3. The Kahn-Tucker doesn't give you, it just gives you the condition for the lambda corresponding to your restriction right here. Okay. So for this, I can only talk about lambda 2. I don't know anything about lambda 1 and lambda 3. Okay, just to be clear about that. They are completely independent. And then you have minus x smaller than minus 2 implies lambda 2 is equal to 0. And then finally for lambda 3, I get minus y is equal to minus a half. This implies lambda 2 greater or equal to 0. And 2, okay, and 2 Sorry, I was daydreaming for a second. Minus a half. That means lambda 2 is equal to 0. Okay, so I got these. This is the whole solution. The actual complementary slackness for each of my lambdas, and then the two derivatives. Okay, everyone agree? I can add like another constraint. I can add 20 more constraints. It doesn't change the way I'm going to do this problem. We're going to write it. It's just purely mechanical. Okay. Now the problem asks us to show that a multiplier must be different than 0. So it's basically asking me, what's this? Okay, we'll change paper. So I'm basically asked to show, they're basically saying, show that a multiplier is different from 0, which is equivalent to show that, it's equivalent to show that you can't have all multipliers 0. That's what they're asking me to do. So in this case, we're just going to say, okay, assume that lambda 1 is equal to lambda 2 is equal to lambda 3 is equal to 0. Okay, and this is where the big problem comes up, because I've seen a lot of papers, and you've done it in this, and you've done it in this homework. Imagine if you are on this with like 3 constraints, it would have been a disaster. And if you write it like this, lambda implies this, etc., then you would just say, oh, lambda 1 is equal to 0, so I'm in this case. Not true. Lambda 1 is equal to 0 can be in this case, or it can be in this case. You don't know. Okay, that is the danger of writing it like lambda implies the restriction. The restriction implies lambda. Okay, so I assume lambda 1 is equal to lambda 2, whatever, etc. So what do I do now? I pull out my Lagrangian right here, and I just replace my lambdas. See what I get. Again, do not replace them in the Lagrangian, replace them in the derivative. So I'm just going to replace them in the derivative. And I get DL. I'm going to copy it here in case you guys don't have it in your books. This is my derivative. Is equal to 0. So at this point, I'll get y minus 2 times 0 times some x plus 0 is equal to 0. So I'll get y is equal to 0. And this is already kind of bad. Like I don't need to do anything more than this partially, because I got y is equal to 0. And at the same time, I know that y has to be greater or equal to a half. So bad. Okay. And I didn't even need to have all of them. It was way too much of an overkill. Obviously, I can go on next and compute x1, replace it in DL. So at this point, the problem is done. Okay. I showed that if all the lambdas are 0, then I'm just gonna get y equals 0, and I need y to be greater than a half. So it's clearly not the solution. It's clearly not what I'm looking for. So it's bad. So it means that this assumption was wrong. Assumption was wrong. Okay, so it means that there has to be one that is different than 0. Now you could have done this, you could have done the same thing in DL dy, ... but again, it doesn't really change. Okay. Questions here? Yes. So for now, I basically just said, okay, if these two are 0, so here's the thing. What I showed here is actually stronger than this. I basically just showed that lambda 1, that one of lambda 1 and lambda 2 has to be different than 0. Okay? So I basically just showed that if I had this, just this thing, just this condition over here, it's still false. Like if I had this. If I just had lambda 1, lambda 2 is equal to 0, that would alone, that would alone generate me something wrong. Just that thing. Obviously, when I add another one, it's going to be even more false. That word. Okay, it's going to be even worse of a contradiction. Now I can plug it in the next one, and I'm going to get something even worse, but I don't need to. It's just that fast, I guess. But doesn't make sense. Like I showed something way stronger than they're asking me show that one out of the three has to be 0, as has to be different than 0. I basically just showed that one out of the 2 has to be different than 0. So I kind of, this is really relaxed. He could have phrased it in a nice way, in a way trickier way, I guess. But this was really, I don't remember. Okay, now we're done with the first point. The second one asks us. Okay, the second one asks us, are the Tucker conditions satisfied at x1, y1 is equal to 3, 2? This is what they're asking me. Are the KT conditions satisfied at this point? Okay. So what do now? You just pull out your Tucker conditions and you check it out. Did I get x1, minus x1 smaller than minus 3? No, sorry, minus 2. Well, minus 3 is smaller than minus 2. So it means that I get lambda 2 is equal to 0. This logic makes sense. Okay. Nice. Now I check for y, and I get, is it true that minus y1 is smaller than minus a half? And I get minus 2 is smaller than minus a half. So it means lambda 3 is equal to 0. Yeah, this is a true. Okay, cool. Now, I need, for starters, like the first check I would do is, I just showed in the previous example that not all of them can be 0 at the same time. So I have 0, 0. I need for lambda 1 to be strictly greater than 0. Now, I can't guarantee it's going to be strictly greater than 0, but I can check if it's 0. How do I check that? I just plug it in. So I get x squared. I need to have x squared plus 18y being equal to 45. And I get 3 squared plus 18 times 2. That's 9 plus 36. That is 45. So it's checked. So it means I am in this case. It means I have a chance for this to be okay. I have not shown it, but I have a chance for this to be okay. I know lambda 1 is greater or equal to 0 for now. So now the last thing I have to check, the only thing I have left to check, is that my system, that these solutions that I got satisfy the system, this derivative system. So so that is true. If they told me that the Tucker are satisfied at that point, then I would automatically say exactly what you said. But they are asking if the Tucker is satisfied at this point. They're asking me to check. Her logic was, okay, I proved in the previous points somewhere on one of these pages. Yeah, I just proved previously that you can't have all of them equal to 0, right? So the idea is that what she was saying, okay, here. What she was saying is that, okay, I proved that they both can't be 0 at the same time. So if I get one of them being equal to 0, then it means that the other one has to be strictly greater than 0. And yes, it is true. The other one has to be strictly greater than 0 for me to have a valid solution. But right now, I don't know. I'm just checking to see if it has a valid solution. So what I'm going to do right now is I'm just going to plug into my system of equations, my derivatives, which I should really order these. Okay. So I'm just going to look right here in derivative of L with respect to X. Oh, apologies for that. Okay, derivative of L with respect to X. And this was Y minus 2 lambda 1 X plus lambda 2. Okay, is equal to 0. Now, is this going to work out? I don't know. Let's see. Y was equal to 2 minus 2 times lambda 1 times 3 plus lambda 2, which is equal to 0, has to be equal to 0. Okay, so from here I get that lambda 1 just has to be equal to a third, which is strictly positive, so that is fine. Everything seems perfectly fine up to this point. Makes sense what I'm doing? So I'm just taking this point that they're asking me to check, and I'm just plugging it into the system of derivatives. If it's the optimal point, it needs to satisfy my system of derivatives. And I plugged it in, and I got that the first equation, dl dx, is satisfied if lambda 1 is equal to a third. It's satisfied. Now I need to see that the second one is also satisfied for this lambda. So what I'm going to do, the second derivative was the derivative of L with respect to y is equal to 2y plus x minus 1 minus 18 lambda 1 plus lambda 3 is equal to 0. So all I have to do right now is plug in my values and check if this works. So I get, and pray to God that it works. So 2 times 2 plus 3 minus 1 minus 18 times a third plus lambda 3, which is equal to 0, gives me 0. I don't know. Is this correct? Let's see. So I get 4 here plus 2 minus 6 plus 0 is equal to 0. So it's true. So now in order to answer my question, are the KT conditions satisfied for this? Yes. How did I check? The lambdas are satisfied. The budget constraint is satisfied, or whatever, this equation is satisfied. And then each of the derivatives is satisfied. So is this a KT valid point? Yes. Okay. Okay. Lucky for you, we have another point to check. So let's see. Okay. I think we're just gonna end it here because there's 6 minutes. And yeah, there's another point. It's right here. Check it if you want at home the same way. But yeah, there's no point in coming back here like for 2 minutes or something. There's the other point if you guys want to check. This is the other point if you guys want to check it. Otherwise, have a great week.